The term stable isotope has a similar meaning to stable nuclide, but is preferably used when speaking of nuclides of a specific element. Hence, the plural form stable isotopes usually refers to isotopes of the same element. The relative abundance of such stable isotopes can be measured experimentally, yielding an isotope ratio that can be used as a research tool. Theoretically, such stable isotopes could include the radiogenic daughter products of radioactive decay, used in radiometric dating. However, the expression stable isotope ratio is preferably used to refer to isotopes whose relative abundances are affected by isotope fractionation in nature. This field is termed stable isotope geochemistry. Stable isotope ratios. Measurement of the ratios of naturally occurring stable isotopes plays an important role in isotope geochemistry. But stable isotopes are also finding uses in ecological and biological studies. Other workers have used oxygen isotope ratios to reconstruct the historical atmospheric temperatures, making them important tools for paleoclimatology. Commonly analyzed stable isotope systems include those of oxygen, carbon, nitrogen, hydrogen and sulfur. These isotope systems for lighter elements that exhibit more than one primordial isotope for each element have been under investigation for many years in order to study processes of isotope fractionation in natural systems. The long history of study of these elements is in part because the proportions of stable isotopes in these light and volatile elements is relatively easy to measure. However, recent advances in isotope ratio mass spectrometry now enable the measurement of isotope ratios in heavier stable elements, such as iron, copper, zinc, molybdenum, etc. Applications. The variations in oxygen and hydrogen isotope ratios have applications in hydrology since most samples will lie between two extremes: ocean water and Antarctic snow. Given a sample of water from an aquifer, and a sufficiently sensitive tool to measure the variation in the isotopic ratio of hydrogen in the sample, it is possible to infer the source, be it ocean water seeping into the aquifer or precipitation seeping into the aquifer, and even to estimate the proportions from each source. Another application is in paleotemperature measurement for paleoclimatology. For example, one technique is based on the variation in isotopic fractionation of oxygen by biological systems with temperature. Species of foraminifera incorporate oxygen as calcium carbonate in their shells. The ratio of the oxygen isotopes oxygen-16 and oxygen-18 incorporated into the calcium carbonate varies with temperature and the oxygen isotopic composition of the water. This oxygen remains fixed in the calcium carbonate when the foraminifera dies, falls to the seabed, and its shell becomes part of the sediment. It is possible to select standard species of foraminiferae from sections through the sediment column, and by mapping the variation in oxygen isotopic ratio, deduce the temperature that the foraminiferae encountered during life if changes in the oxygen isotopic composition of the water can be constrained. In forensic science, research suggests that the variation in certain isotope ratios in drugs derived from plant sources can be used to determine the drug's constitutive origin. It also has applications in doping control, to distinguish between endogenous and exogenous sources of hormones. Chondrite meteorites are classified using the oxygen isotope ratios. In addition, an unusual signature of carbon-13 confirms the non-terrestrial origin for organic compounds found in carbonaceous chondrites, as in the Murchison meteorite. Bibliography. Allegri C.J. 2008. Isotope Geology. Foragy, Mensing T.M. Isotopes, Principles and Applications. Hoefs J. 2004. Stable Isotope Geochemistry. Sharp Z. 2006. Principles of Stable Isotope Geochemistry.